We are here to talk about Thomae's function, which is terribly interesting. And that's defined to be 1 if x is equal to 0, 1 over n if x is a rational number written in its lowest terms, and you have to write it where the denominator is positive, which is always possible. And 0 if it's irrational. So first of all, let's just figure out some values. T of 0 is easy enough to figure out. It's just 1. T of 1, well, I can write that as a fraction. That's 1 over 1. And this says it's just 1 over the denominator equals 1. Similarly, T of 2 is equal to 2 over 1. That's a reduced term fraction, which equals 1 over 1 equals 1. And T of 3 is equal to 3 over 1. But that's 1 over n, where n is just equal to 1. So for the integers, you always just get a value of 1, because you would just write down the integer divided by 1, and then the denominator is 1. T of pi is going to equal 0, because it's irrational. T of e is going to be 0. T of square root of 2 is going to be 0. Any sort of irrational number is going to have a value of 0. That's easy enough. The interesting part is now with the rational numbers. T of 2/3 is going to equal 1/3, because it basically says ignore the numerator and just do 1 over the positive denominator. T of 5/10, oh, wait, we have to reduce 5/10. T of 5/10 is, that's 1/2, which equals 1/2. T of 3.1 is T of 31/10. That's reduced, so that gives me 1/10. T of 3.14 is the same as T of 314 divided by 100. That's not reduced, so let's reduce this. 157 divided by 50. There we go, that's reduced. So that gives me 1/50th. And similarly that's T of 3141 divided by 1,000 equals 1 over 1,000. So that's how you compute using this function. But let's graph this now. So here's 1, 2, 3, and I'm going to make the fourth really exaggerated. 1, 2, 3, 4, and here's my value of 1. Here's 1/2. So here's what we see. The value of all the integers is just 1. So maybe I should graph this in red. So I get, at every integer value, not to scale there, I get that. At every irrational value, I get 0. So here's pi. Here's pi, here's e, here's square root of 2. Those values are all 0. Screwed up there. I'll erase in just a second. Those values are all just 0. Okay. Now the interesting thing is with the irrationals, or with the rationals, sorry. So here's 2/3. I need a pencil here. Here we go. So here's 2/3. That says you go up to 1/3, which is right about here. 1/3. I should do that in black. Here's 1/3. Here's 2/3. Here's 1/2. Here's 3.1. Here's 3.14. Here's 3.141. So let's graph all these. Okay? 2/3 goes up to 1/3. 1/2 goes up to 1/2, like so. 3.1 goes to 1/10, which is going to be like right there. 3.14 is 1/50th, which is down there. 3.141 is going to be 1,000. So what you get is, as you get really close to an irrational number, you get that the rationals go down to 0. The closer you get to an irrational number, the bigger the denominator has to be. Because, I mean, basically, if you take out the decimal expansion, they're going to, as you get closer and closer, they're going to agree on more and more decimals, which means you need a big power of 10 to the denominator, which means it's going to go to 0. So as you can see, whenever you're at an irrational number, if you take any epsilon neighborhood around it, all the values are going to be really close to 0 because the denominators are all going to be really small. So any epsilon neighborhood around it is going to be close to 0. But all the rational numbers are going to be far apart. So they're discontinuous to the rationals, continuous to the irrationals.